Okay, everybody, time to talk about time series designs. I know the title says interrupted time series, but hey, not perfect. Anyway, so we're going to look at time series designs, and specifically, we'll spend most of our time on the interrupted stuff. But before we go further, I want you to look at that picture a little closer. All right. I took this one leaning out of a car on the way back from, I don't know what kind of car it was, a 4x4 of some sort, leaning out of that rig on the way back from Jalalabad to Kabul over in Afghanistan. And they had this beautiful highway. As you can see, it's actually a well-paved highway, nice and smooth and all that stuff. And then all of a sudden, there's these gigantic speed bumps that if you didn't have a 4x4, you couldn't get over them. And cars that you can kind of look off to the side there and you can see where there's some tracks going off around all the dirt. And that's where cars would have to actually drive through the fields to get around these things. Why they put them there, I have no idea, but it's an absolutely great representation of an interrupted time series. You can see the road there. It's long, it's straight, and you're just cruising along doing your 80, 90 miles an hour or whatever, and then all of a sudden it's interrupted. And then after that, you just cruise along again, right? So that's a good example of an interrupted time series design. So we'll get into it a little bit more here, and I got some real interesting data for you on this one, and some real examples, and we'll jump over to YouTube, and you'll also see that in the Blackboard course, there is a YouTube video linked in there. I'm going to go over that a little bit, but I'm not going to watch the whole thing with you on the lecture, because first off, it looks better than the way I'm going to capture it for you on here. And second off, it's like 3 minutes long, and I don't need that much to make my point, but it's useful to watch the whole thing. So, all right, let's get rolling. Right off the bat, time series. What we're talking about here is long-term stuff, right? Long-term assessment. More than 100 measurements is kind of the rule of thumb that I think about. And we're going to repeatedly measure the same thing, just over and over and over and over and over and over and over again, right? And we're going to look for changes over time in that. And we'll talk about the types of effects that you can get in a minute. A lot of times you're just using the same people. You're just sticking with those same folks. You track them for a year, 2 years, 3 years, whatever it may be. And you can just see how they change over time. You can also use different people. This kind of falls in the category of cohorts, right? In a sense, or you can just look at different people altogether. Think of a law change. So we look at the driving records of people from 1995 to 2005. Then maybe some law happened in 2005, and we can look at driving records from the end of 2005 through 2015 or whatever, right? It's not going to be the same people, but you can get an idea what's happening. So even though the data is coming from different individuals, that's okay. It all depends on what your data point is, or the data that you're interested in, as to whether or not you're going to get it from the same folks constantly over their lifespan, or however you want to measure that, or if you're going to get it from different folks. So it works either way. There's no problem if you do it with the different folks. So if we measure if we measure folks or whoever just repeatedly without doing anything, that's just a time series design. Right? That's really simple. All we're going to do is take a measurement this month and next month and 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 month, and we'll be able to track how you change throughout your lifespan. There's been quite a bit of this done with alcohol use. It's been a really common sort of thing to study, especially at the university level. And if you start to track how people's drinking changes, their drinking patterns change over time, you see some really interesting data. And some of that data basically says that once you're out of those college age years, your drinking tends to decrease anyway, right? So there's a big push on getting people to do binge drinking interventions and reducing drinking at the college level, but there's quite a bit of evidence, time series designs, that say that it's only a temporary effect anyway, and it goes away naturally. So is there a problem with it? Yes. Are there deaths that happen and people get seriously injured because of it? Yes. So in other words, we should be thinking about reducing it, but the problem might not be as long-term as what we often think. And it also happens to follow for people that aren't in college as well. So they tend to drink more during a certain time of their life, and then that tapers off as time goes on. But an interrupted time series is something a little bit different. This is where we would actually do some sort of intervention. So we would make, let's say, 50, 60 measurements, and then we would change something. And then we would make another 50, 60 measurements. Right? It's still a fancy A-B design, right? It's that single group pre-post, right, that we talked about before, but it's single group with post, right? So you get all these measurements, tons and tons of measurements. So then you can start to see if things changed at the time that the intervention happened. So if the pattern that you see changed after if the pattern that you're seeing changes after that intervention, then you're definitely, no, not definitely, but you're reasonably confident that your intervention might have had something to do with it. The most simple one to think about in terms of an interrupted time series is something I've already talked about, which is a law change. Because we've got all those police records, right? We've got all those insurance data records. We've got all these records that exist out there that we can use, and we can see how many accidents were occurring before we started the laws on no texting while you're driving. So we can measure a certain number of years and look at the number of accidents, and we can even break it down to the number of accidents in which a cell phone was contributed to that accident, right? And then the law happens, no more texting while driving, and then we can measure, then we can capture that same data again and then compare it to the initial data and see if there's different trends. Sometimes there is, sometimes there isn't. Sometimes laws have no effect, other times they do. And we're going to look at something that happened here in a little bit that kind of makes that point. So I got a little ahead of myself there. So that just simply adds an intervention component. That's all it is. At this point, we're not talking about adding any control groups, but down the road we will. We'll talk about how you can add a control group for this. You can do interrupted time series. Probably my favorite type of interrupted time series is one that I don't even think your book really covers. It might have covered it in the last chapter, but where you do a cohort interrupted time series, which seems really odd. But basically each cohort serves as a control for the previous cohort, and then you can interrupt each cohort, if you will, and see what sorts of changes are happening. Or you can just interrupt one cohort. There's a lot of really cool things that you can do with time series designs, because you do get so many measurements, and it becomes very sensitive to any changes because you can see those changes, and your book goes through a bunch of different graphs for you to see how to interpret those changes, and I'll kind of summarize some of those here next. All right. So essentially what we're going to do to see if there's an effect in a time series is all we're going to do is compare the data prior to the interruption to post-interruption. And a lot of times, for analysis reasons, this is done visually, and there are plenty of statistics that we can use, and we'll talk about those statistics in a minute, but they're very problematic, and the statistics are questionable at best for how to interpret this stuff. And I'll tell you a little bit how I've done some of these things, and there's some problems with how I did it as well. So just know that, typically speaking, the easiest way to interpret this stuff is a visual analysis. Is it the most accurate? Maybe not. But I have that same reaction to the statistics that we would use for this as well, is that it might not be the most accurate way to do it. So probably a combination of both. You can do that ocular analysis, so you can look at the data, and then you could see if the statistic confirms it, or vice versa. Run the statistics and then look at it visually and see if those two things match up, if they look like they're going together. So essentially all we're going to do is evaluate a trend. That's the most basic way to interpret this. If you have a strong, steady, increasing trend before the intervention, then you start the intervention and everything flatlines. So now that's not strong. Now it's not a strong, steady increase, and it actually whoever it is stops, changing their rate of behavior or rate of whatever it is that you're measuring. Then you might conclude that that intervention halted whatever that increase was, or maybe it was flatlined and then it increased, right? Or maybe the rate of change changed. Right? So a change in the rate of change, essentially. So if you think about measuring learning, right? So think about a kid that's behind the curve in terms of their reading ability, or the vocabulary is an easy way to think of it. So think of a kid that's behind the curve in terms of vocabulary. They're still learning vocab words, but they're learning them at a certain rate. So you can measure that rate. We can track that. And it would be a steady increase. But then you could start an intervention, right? And you could increase the rate at which the kid is learning. Then you would have an increasing line followed by an intervention and then a steeper increasing line on your graph. And you might be able to conclude that that was the intervention that caused that. The other thing that you can do, and I've never actually done this one, so this is one I don't have personal experience with, but it makes perfect sense, is evaluating the variance. Right? So think about how, your book goes through this as well, but if you've got some data that's really stable, right, during all those pre-measurements. So it's flat, 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 flat. And then all of a sudden you do an intervention, and then the data goes really high and then really low and really high and really low, and it's not stable anymore. And you have to ask the question, you have to address the question about if the intervention caused that instability in the data. In other words, did it cause variance? Or you could go the other direction, right? You have a lot of variance early on, and then you start an intervention, and you then see if it's stabilized after that. And there's a kind of a funny story about that particular example that exists in the pro basketball world. Shaq used to be an awfully inconsistent free throw shooter, right? So you think about all the time that Shaq was shooting free throws, and he wasn't doing very well. And then all of a sudden he started doing his, if you guys remember the commercials, the taco neck thing. He'd kind of bend his head in a funny way. And his free throw shooting was dramatically improved. So think about the variability there. He made some shots this week, a few shots the next week, and so on and so forth, up and down and up and down and up and down, just wasn't consistent. Then he tried a new technique, in other words, an intervention, and then it stabilized. Right? So he did much better consistently. He was much more consistent since then. So that's the type of thing that we're thinking about in terms of variance. Right? We could probably make an argument for the same thing that happened to Tiger Woods. Definitely increased his variance after the whole drama of the accident and the divorce and all that other stuff that happened to him, the knee injury and all those things. That's an example of how that variance can change, and you can pick that up using a time series design. All right, let's look at those analysis problems that I was mentioning previously. Ultimately, the issue here is that each measurement is highly related to the previous, and in other words, it's typically very highly correlated. And this is called autocorrelation, and we'll get to that here in a second. But the idea is that, let's say we've got 50 measurements out front, right, and on the pretest section of our intervention, or sorry, geez, just losing the words today. During that pretest section of our design. So when we do all those measurements are related to each other, meaning that your score at time 2 or time 3 or time 4 is at least partially explained by your score earlier on, because there's a certain amount of whatever your score is that isn't going to change. You're going to stay the same, and that stay the same part is what becomes a problem, because in most of our statistics we have an assumption of independence, and that assumption of independence means that each measurement is independent of the previous measurement. In other words, it's not influenced by the previous measurement, and in this case it kind of is, right? It's all the same thing is influencing each score or each measurement that you have, and that becomes a problem. It's called autocorrelation, where all the scores autocorrelate with each other. So score 1, score 2 would be highly correlated, score 2, score 3 would be highly correlated, and so on and so forth. Right? Statistically, it's a bugger to deal with that, and if you don't know that it's going to go on, if you're not familiar with autocorrelation and you're not prepared for it, then your statistics will be overly sensitive. In other words, you'll get some type 1 error going on, right? And if you recall, type 1 error is finding something that isn't there. It reduces the amount of variance you have, but that's not a natural sort of reduction in variance. So remember we're talking about in that formula we always divide by within groups variance or the unsystematic variance. Well, autocorrelation stuff automatically reduces that unsystematic variance. So now you're dividing by a smaller number in that formula that I gave you, and that's going to give you a bigger number on the outcome, right? And that's going to make it seem like you're significant when you really aren't. So that's the problem with autocorrelation. And right off the bat, there's a couple of things that we can do to deal with this. Number one is the specific statistic that's becoming well understood, and it's becoming more and more used for a lot of reasons, and it's being adopted in psychology as well. But it's autoregressive integrated moving average. Don't worry, I'm never going to test you on it. But the idea is that you can track those averages as they change rather than looking at each individual data point. You can kind of lump stuff together into chunks, and there's a little section on your book that kind of describes how and where it's used. And I'm not going to go into it any more than that, but that's just one of those things that you can do. So there are some stats that you can use to do this. But the take-home message for you is when you're reading an article and you see that they're doing a time series design, if they're not using ARIMA, which is what this is, auto-regressive integrated moving average, right? If they're not using an ARIMA statistic, you should probably question their results, because that it may be that they have this autocorrelation issue going on, and you would just have to be a little bit cautious with your interpretation of what they have if they're claiming they have significance and things like that, and they didn't use some special statistic in order to address the autocorrelation issue. Kind of how I did this, I mean, I used to collect data on sexual behavior and drinking behavior in college students, and I did that for years, and I still do it to some degree. And one of the problems that you have is that you capture data every week. So essentially, we always have this time series thing going on, and we have a new interruption every week, and that's really beside the point. But the idea is that all of the data points are related to each other. And I used to do this in a semester system, and so we had 16 weeks that we would record data for. So ultimately what I would do is I would break it down into chunks. I would take the first half of the quarter, compare it to the second half of the quarter, and average those all those data points at time one. You know, those first 8 data points, I would average them and get a score. And in the second 8 data points, I would average them and get a score. Then I would compare those two averages, right? So essentially I had time 1 and time 2, but time 1 was an aggregate of 8 scores, and time 2 was an aggregate of 8 scores. And I've analyzed it in a lot of different ways in order to get it into the right type of statistic that would allow me to do that. I've done it with where you would do 4 weeks at a time. So you got an aggregate score of 4 weeks, another 4, and another 4, and another 4. And at that point, you can use statistics that are designed to do repeated measures stuff, but without the problems of having like 16 different measurements in there. And there's some, I'm getting way beyond where we need to be here, and we'll cover some of that later on in a course. But ultimately what happens when you get all those repeated measurements, you run into some problems, not just with autocorrelation, but with some other things. So things like a repeated measures analysis of variance, which is a special statistic to capture repeated measures data, it becomes not as useful as what it could be. So you aggregate it, you break it down into these chunks. And so I could break it down into 4 chunks from 16, and then look at it and see how people changed over time. And there's a lot of ways that you can use that. So that's kind of the trick that a lot of people will do when they have time series analysis. And it makes some sense. There's some problems with it because you're losing data every time you average something, you lose a level of analysis. You lose some of that detail and that granular focus on the data. So anyway, that's okay, but it has its problems, and all these things have their problems. So the ARIMA is probably the most up-and-coming statistic that's being used with this. I don't have any experience with it personally. It takes some pretty special software to do it, and I've never had the funds to play with ARIMA software. So anyway, all right, let's look at some of the designs that we can do here specifically. A simple interrupted design is as I've described. It's basically one group, and we're just going to compare those changes in the data from pre-intervention to post-intervention. We're going to look for that trend analysis. Right? So let's look at something kind of cool here. The Kyoto Treaty, for those of you that recall what that is, was basically where a bunch of countries, in fact everybody but the United States, got on board and decided to reduce, the CO2 emissions and things like that. So it's trying to help the environment, right? So what we've got is, we can talk about the types of effects that are here. Was there a weak effect? Right. Was there a delayed effect? So let's actually look at the data, because I have the data here, and the data that I'm going to show you is from I can't remember the NOAA or one of those NOAA, National Atmospheric and Oceanography, whatever. Anyway, the recordings that I have, or the data that I have, are the actual CO2 concentrations measured on a month by month basis from like 1958 up until current, and I've got this data current up through June 2012. And in here I put the Kyoto Treaty stuff so you can see that simple interrupted design. So let's look at it, and then we're going to also interpret it in terms of the weak effects and delayed effects. So I will pull that up right now for you. Okay, pay no attention to my hard drive in the background, or my computer screen in the background, my desktop. Just focus on the data that's in this graph. And as you can see, this is one big graph. And we'll get into we'll zoom in on it here in a minute so you can see exactly what's going on. I'm going to make it a little bit bigger so we can actually get a decent sort of analysis when we look at this thing here. So I'm just going to fill up the screen with it, I guess. That'll make it look a little better at least. Still have to play around with it, but that's okay. At least you can't see my ugly desktop. All right, so let's get familiar with the data here, and let's start looking at what's actually going on. So I'm going to zoom in quite a bit. And you can see, that's kind of funny looking over there. There we go. All right. So you can see what's happening here. We've got data points for each month, and this is CO2 concentrations in parts per million as measured in Hawaii, right, which is close to the equator, a great spot to measure these things for several reasons. All right, so we're starting in 1958, and we see this little cycle. Every break is a year. I just did that so it's easy to tell where the years are. It's not like there's a missing data point, right? So it's just these years. So this is one huge time series design. Right? It's not, at this point, it's not interrupted. We've just got this time series design going on, right? So let's zoom in a little bit more here, because I want to show you some of the problems that exist with time series design or without time series design. Let's say, okay, now we're looking in February 1962. So we've got this. There's 62. So here's January. Sorry, this is the January data point. February, March, April, May. You get the idea. If we just captured the data from May through September, it would look like there's this nice decrease. You can see that nice decrease right there. But one of the cool things about time series design is that it allows you to capture these cyclical effects, right? So what we see constantly are these cycles, right? In CO2 concentrations, it drops from summer to fall, and in the northern hemisphere, keep that in mind, and then it increases, and it drops from summer to fall, and then the CO2 concentrations go up. And the basic idea is that why does that seem to follow the patterns of summer and fall, and winter and spring, and it follows those patterns, right, with these increases. And it matches the northern hemisphere times, not the southern hemisphere. Well, it's because if you take a look at the globe, a majority of the greenery on the planet, like the majority of the trees, are in the northern hemisphere, right? So when you think about what's happening during summer and fall in the northern hemisphere, is that the trees are growing, right? The green, it's all green, everything's growing, it's basically absorbing CO2, right? So as a result, your CO2 concentrations are going to go down. So if you look at a very detailed analysis, a detailed time series design, you'll see that cycle, and whoa, sorry about that, and you do see that cycle right here. So let's just keep looking at it, and notice that cycle is the same year after year, but you're getting something else. You're getting this general increasing trend, right? So keep in mind that we're looking at, there's 320 parts per million. Okay, that line is 320, there's 330 parts per million, and just keep an eye on what happens with our data here. So I'm zipping up, there's 1970, 72, let's jump up into the 82. Okay, so right in here is 1982. Just a constant, continuous increase. Right? So this is some really, really clear time series designs at this point. It's a simple design at this point. It's not interrupted. Right? We're going to get to the interrupted point here in just a second. So we're at 94. Here we go. Now in 1997, all right, where are we at? Yeah, 97 is the Kyoto Treaty, right? This is when it was adopted, was that month right there. So that's when it's adopted. That wasn't when it was enacted. Right? So let's just, at this point, we don't, in my opinion, we wouldn't have it interrupted yet, because just because it was adopted doesn't mean anything's been done with it. So the point at which something's been done with the Kyoto Treaty, to me, is the point at which we should think about it being an interrupted time series. So we've got those hundreds of data points from 1958 on a monthly basis all the way up until February 2005 right here. So January of 2005 is that data point. Kyoto went into effect in February 2005. So if Kyoto had an effect on CO2 concentrations in the planet, we should see some change coming up. So let's see if we do. What do you think? Do you think there's change there? Do you think that trend stayed the same? So keep in mind, there's where Kyoto was put into place. Let's back it up. If you ask me, I say no. It doesn't look like there's a change. That trend, that general increasing trend, stayed the same, right, throughout that whole time. So you've got this general increasing trend from here. In fact, we're not even at the full view yet. There we go. It's huge amounts of data. So you see that stuff just going up and 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 going, and then it continues to go up. If Kyoto had an effect, you would have expected this to flatten out a little bit over here. Not the monthly cycle, not those annual cycles that you see, but you would have expected it to flatten out a little bit here. Now, this isn't the full story yet, because we could have been working under a delayed effect, right? So, and sometimes that happens where you do an intervention or interrupt the time series, and the effect only shows up 6 months later or a year later or 2 years later. But oh my gosh, that was February 2005, right? We're all the way up to 2012 here. Okay, and to me, and again, this is no statistics, this is just a visual analysis, it doesn't look like there has been any delayed effect at all. Okay? So would you conclude that Kyoto worked? Was it a bad thing? I don't know. Maybe the U.S. was right not to sign on. Maybe they were wrong not to sign on. Maybe if the United States signed on, that we'd see more of an effect here. Who knows? It's just guessing at this point. But the idea is that it doesn't seem to have changed the CO2 concentration thing. Right? So then you got to ask the question, maybe it was a weak effect. Maybe it's just very, very minimal, and it's going to take a long time to see that. And not just delayed, but weak, so it actually slows it down. I don't see a weak effect here either. Right? There's some funny flat spots in the data, like right there. But notice those funny flat spots also showed up previous as well. So I don't think that's a Kyoto effect. This little set of data, right, those 3 data points, which are pretty flat compared to all the other stuff. So I'm not so sold. Based on this data and this data alone, it doesn't look like it's had the impact that we would have hoped it would have. So, all right, let's jump back to the other slides here. There's one more set of data I want you to look at, and that's the CO2 concentration stuff, not just with the Kyoto Treaty, but there's some other longer history type things that show an even bigger time series. And this is pretty overwhelming data. It takes about 3 minutes to get through it. I'm going to just zoom in on a couple of parts and explain what's going on in the video, and then you can watch the video on your own, and I'm going to zip to the end of the video and go through and look at this time series things and how you can interpret time series designs and some cool data that's associated with it. Okay, we'll jump back over to a video now. Okay, we're here. We've got the video going. Now, keep in mind we're looking at same data here. This is the same data, but it's collected from a lot of different data points. Remember what I was telling you, that where my data was collected from the graph we just looked at was in Hawaii. That's the red dot. So watch that red dot, and you'll see how that interprets. All these other dots are from different parts of the planet, so you get an idea of where these measurements are being taken. This data, this particular graph, starts in 1979 and goes forward, and you'll see what happens here. Here's your monthly cycle, those annual cycles. Right? So you can see the data on the left here. It's bumping up and bumping down and bumping up and bumping down, and it's doing all that stuff. So that's giving you those comparisons and showing you where the kind of the shadowed line there is where it first started. And as you go on, you can see what's happening. And then over here on the right, it's showing you this increase. That's the exact same data that I showed you if you think of the red dot, right? Because the red dot was the one that I was demonstrating for you. So the red line here is actually that same exact data. It's from the same data source, so it's no different. They have it on a different scale, so it looks like it's bigger, right? So it looks like there's more of an effect. It looks steeper. That's for drama, okay? This is the problem that you have when you do graphing and you screw up your axes. It starts to look overly dramatic. But of course with mine, you saw how big that graph was. You'd have to make it dramatic in order to see what's happening. So anyway, that's going to just continue on there for a while. So let's just zip forward, because what I really like about this data is that it doesn't just show you what happened from 1958 on. It shows you what happened before that. And the way they have plotted this, it really starts to look pretty cool. So I'm going to zip up to, let's get back to 1980 here. Here we go. So okay, this is where the red line is where it started. Green line, we're going backwards, right? So you're looking, there's the end of the data set from Hawaii. Okay. Look at that. I'm going to pause that here, because what we're talking about is the pre-industrial the Industrial Revolution. After the Industrial Revolution, you start to see this dramatic increase. So if you look at the years here, so this is the year 1500, right out here is 2010. So you've got these, and this is again your parts per million plotted on this graph over on the right. So it sure looks to me like something happened right about here because it was nice and stable, right? So you get that 278 parts per million, and then right about here something happened. Well, that happens to be about the Industrial Revolution, and then boom, it shoots up. It's unbelievable, and it's been exponential ever since. And that is one crazy exponential line. So that is a hugely steep thing, and again, we're looking at a major time series design here. And so you would think that this interruption that happened right here, something that happened along these lines, might have driven that change. Well, it makes sense. With the Industrial Revolution, we're going to start pumping all sorts of stuff into the environment, and CO2 is going to go up, right? So let's keep watching, though, because one of the concerns that people have with CO2 data is that, oh, these cycles are just natural, right? So again, what you would think is that with a time series, you would be able to capture those natural cycles. And can we see those? You saw the cycles from 1958, and those are all in this red line up here, right? All those cycles are what's going on up in that red line. And so it looks nice and straight, but in reality, it's very cycled. So the question, and some of the opponents of this type of stuff, and these the opponents, and they're not even scientists, they're just people out there that don't understand the data, will argue against this stuff because, oh, well, the Earth's just going through a natural cycle. All right, fine, let's look. Again, we're still looking in pre-industrial stuff. We're at 500 here. So now we're at year 0. Now we're going to make some pretty cool changes. Now we're going to back up 4,000 years, 5,000 years, 10,000 years, 15,000 years, 20,000 years back, 30,000 years back, 40,000 years back. So those natural changes, those natural cycles, they're there. We're going to keep going. And this is going to zip all the way out to 800,000 years. There's your natural cycle. Look at that. There's your high point. 270 parts per million. Almost 300 here. So these low spots, those are your ice ages. So that's that cooling and warming effect that the planet has, right? But let's go back 800,000 years. Up, down, so you've got these big cycles. Well, what in the world happened right here? Whoa. Oops, let's back that up a little bit. What in the world happened right here? That orange is the pre-industrial, that's the Industrial Revolution. Okay? So, pre-industrial revolution, we're averaged at about 278. Ice ages, they're nice and low, right? Which is what you'd expect. But up here, it's gone crazy. So something is happening in this area, okay? And that is a very clean, very beautiful sort of a time series analysis that shows you that something interrupted this process, because this process for almost 1 million years was pretty steady. And it's fairly flat. It's generally increased a little bit, but look at that nice cycle. It's a nice clean cycles that you had ups and downs and ups and downs, and now this. Okay? And this data is actually a little bit old, January 2011. I've got data on that other graph all the way up to 2012, and we're skirting with 400 parts per million now. Now let's think about that. In history, there was never above 300,000 parts per million in terms of natural history of the Earth, right? So as we move on, we get up there. So I'm getting a little bit onto a political thing here, but really not. I mean, some people think this stuff is political, but it's not. And if you look at the data, there's no politics involved. This is clear. So a quality time series analysis can show you some really, really interesting stuff. And this is one of the most interesting pieces of data that I've been able to get my hands on to demonstrate how time series can work. Okay, we'll go back to the slides. All right, let's look at some of these threats to validity. Number one, right off the bat, when you're working with people, of course, you don't have this issue with CO2 concentrations, but with people, you have the testing effect, right? You're going to repeatedly measure these people, so as a result, they're probably going to become familiar with that testing measurement or that testing tool somehow, some way. Who knows what, how they can be affected by it, but it could ruin your data. It may not ruin your data, but it could. And with threats to validity, the issue is that it can. It's not that it did; it's that it can, and you can't rule it out. So testing effects are a dramatic problem. Are a dramatic problem with time series designs. Maturation, people might be naturally changing, right? And if you're just doing a regular time series, then that is a really big issue. But when you do the interrupted time series, it's less of an issue, right? If the change in the slope or the change in that trend happens right away at the same moment that your intervention happened, then it's going to be hard to justify that as being just a natural maturation. Right? It could be, but it's not very likely. So the interrupted helps with that, but not, it doesn't completely get rid of it. History effects, something may have happened during that time that caused a change. Maybe 9/11 caused a change in people. Maybe the Mount St. Helens caused a change in folks. Who knows what caused a change? So the history effects are a major issue here. Instrumentation is an obvious one. If your instrument is getting weaker or less sensitive over time, or overly sensitive over time, then you can run into some problems. This is actually an issue with the CO2 data because we have to use ice cores to measure that stuff that's from 800,000 years ago. So the question is the instrumentation accurate? And there's been a lot of studies on that. And generally speaking, yes, the instrumentation is very accurate. It's been confirmed in multiple ways. So it's not something that's really arguable, but it's something that they worry about and they test. So remember earlier we talked about jumping into the threat and digging into the threat and trying to rule it out. That's what goes on with instrumentation stuff, especially with the CO2 data, because it's such a hot topic. Ha 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 ha, no pun intended, kind of. But anyway, you go in there and you actually look and you see, okay, is my method wrong? Is my instrument broken? If it is, it's giving me inaccurate data. So those are the major threats to validity with this stuff. There's others. Right? There's better ways you can move on and do stuff with this. You can add a control group, as we talked about. The problem is you still don't have random assignment, so you're still not getting that really high quality causal inference, but it's not bad. You can add non-equivalent dependent variables. This is kind of a cool one. Basically, you measure twice, right? You measure two things every time, and every time you do your data points, you get two lines on your graph. And the idea is that one should change at the intervention and one shouldn't. Your intervention should affect one of those. So they're non-equivalent dependent variables. And we looked at those previously with some other design types, and it just helps you isolate what the effect was, because that might get you to rule out maturation, it might get you to rule out history effects and those types of things. Because if the intervention is designed just to affect one thing, and that one thing is affected after your intervention, then you can have some confidence that the intervention did do what it was supposed to, and it's not some threat to validity. There's a ton of problems with these things, and you can flip through them in your book. What I've got here basically says don't use short time series designs. Right? There's other problems with short time series designs, and there's benefits of using short time series designs, and you can read about them. I can't explain it any better than Shadish, Cook, and Campbell can, but the idea is that if you do too short of a time series thing, you're never going to catch those cyclical effects. So think of the CO2 data. If you just track it for 6 months, well, it's going to look like it's decreasing or it's going to look like it's increasing dramatically, and that's not an accurate way to look at it. So that short stuff is not a really good way to go. I think 100 measurements is kind of the standard here for time series stuff. So that's what you want to think about, is a lot of these things to capture those cyclical effects. A lot of times you're going to use archives to do this type of research as well, but you have problems with archives. There's missing records. You might not get access to it. If it's public records, that's fine, but if it's private data, if it's private companies, they may not want to give you access. They may fear what you're going to do with it, so you may not be able to actually get it. Right? It might not be on the right scale. You maybe want to analyze responses per minute. For example, I've done some research on responding on tests in a Blackboard class, or taking tests on Blackboard, and Blackboard recorded it in terms of when you started and when you finished your test, and it was easy to analyze it in terms of days, right? So I could say, on day 1 this person started their test or attempted their test. On day 2 they attempted it again, and day 3 they attempted it again, and so on and so forth. But what I really needed was a minute-by-minute analysis. You may not be able to get that minute-by-minute analysis depending on the archival data that you have. It so happens that I got lucky, and with Blackboard I could get the minute-by-minute analysis, and it was in my archive, and it was my own data, so I was lucky there. But that's not always the case, right? So depending on what you're looking for, you may not actually be able to get those detailed results. If you think about law changes and accidents and things like that, and you're looking at maybe the cell phone laws and the driving, and if it's not recorded what the cause of the accident was or what influenced it, then you just know there was an accident. You don't know it was caused by a cell phone. So Anyway, that's about it for time series stuff. There's a little more in your book, and feel free to read up on it, ask some questions, and we can talk about it. I hope you enjoyed the CO2 stuff. I thought it was kind of cool to look at that new video and go over those things. Take care. I'll see you soon.